Hello everyone, this is Professor Roman. Welcome to the second video in my video course, An Introduction to Discrete Mathematics. Last time I talked about sets, the foundations of mathematics, and the Zermelo-Fraenkel axioms of set theory. I want to talk now about a concept that will be very important to us in many portions of the book, especially when we talk about counting techniques, and that is words over an alphabet. Here's the official definition. If sigma, this is the Greek uppercase letter sigma, is a non-empty set, then any finite sequence of elements from sigma, written with no commas or other punctuation, just placing the symbols one after the other, is called a word or string over sigma. The length of a word is just the number of elements in the word. And there is a special word that has no elements. It's called the empty word, and we're going to denote it by the Greek letter epsilon. That's quite common, I think. In this context, the set sigma is called an alphabet. The elements of sigma are called letters, and the set denoted by sigma star of all words over sigma is called a formal language. So this is a very general concept, but extremely useful. Let me give you an example. Suppose the alphabet is this set. Then these are words over this alphabet. Letters can be repeated as many times as you want. There's no restriction on that. And I suppose it's worth mentioning, sometimes I see a little confusion. The fact that we use the term word doesn't mean these have to be words from any particular language. This is a very simple formal definition. Words can be any strings of letters from the alphabet. If W is a word of length n, then the prefix of W of length k, and k will have to be less than or equal to n, is just the word consisting of the first k letters in W. So for example, if this is W, then the prefix of W of length 4 is just the first 4 letters in the word. One of the most common alphabets in both mathematics and computer science is the set consisting only of 0 and 1. A word over this alphabet is called a binary word. So here are some examples. The individual zeros and ones in a binary word are called bits. And binary words of length 8 are referred to as bytes. Now in mathematics, binary words are particularly important in the study of error-correcting codes, and that belongs to a branch of mathematics known as coding theory. In computer science, binary words primarily take their importance from the fact that computers store and manipulate data in the form of binary words. But there is a potential bit of confusion here with the term word. In computer science, when it relates to a specific computer, every computer has what is called a word length. And that's generally defined as the length of binary words that can be directly manipulated by the central processing unit. Word lengths for personal computers started at 8 bits and slowly evolved to 16, 32, and now 64 bits. So if you hear the term word used in the context of computer science or a computer, it's a fixed length word. whereas in mathematics, the term word does not imply any particular length. Words over this alphabet, 0, 1, and 2, are called ternary words, and here are some examples. I wouldn't have brought this up, except that these will be useful in some exercises and examples. So that's the extent of which we'll use ternary words. And finally, if sigma is an alphabet, we're going to use some notation. Sigma sub n is the set of all words of length n over sigma. So sigma naught consists of just the empty word because that's the only word of length 0. And gamma sub n will denote the set of all words of length at most n. Well, now it's time to give a formal definition to the concept of a subset. So suppose that A and B are sets. A is a subset of B, and we'll denote that using this symbol if every element of A is also an element of B. And in this case, we'd also say that A is contained in B, or B contains A. We would also say that B is a superset of A. And this is another notation for saying that B is a superset of A. A is a proper subset of B, which I'll denote using this symbol, if A is a subset of B but not equal to B. So all subsets of a set A are proper subsets except A itself. It's a bit unfortunate that the notation I've just given you is not entirely universal. Some mathematicians will use this symbol, which we use for proper subset, to mean any subset. And then we'll have to use a different notation for proper subset. But not to worry about that. We'll stick with our notation, except it's important to know this because if you read other books and you see this symbol, you'll have to check and make sure you understand what the author means by it, subset or proper subset. By definition, the empty set is a subset of every set, and every set is a subset of itself. Some quick examples. We have this chain of subset relations. Actually, these are proper subset relations. Natural numbers, proper subset of the integers, proper subset of the rational numbers, proper subset of the real numbers. If sigma is an alphabet, then gamma sub k is a proper subset of gamma sub n when k is less than n. We've already discussed power sets. The axiom of the power set guarantees that they exist. Here are some quick examples. The empty set has only one subset, so its power set is the set containing the empty set. And over the years, I've noticed some students get a bit confused between this and this. This is a set that contains one element, which happens to be the empty set. So this set is not the empty set. It has one element. This is the set that contains no elements. So these are quite different things. A singleton set has two subsets, the empty set and itself. A doubleton set has four subsets. A set with three elements has 8 subsets. And we're going to see later on that a set with n elements has 2 to the n subsets. And we'll in fact prove that by a couple of different means when we talk about proof techniques. The cardinality of a set is the number of elements in the set. So we'll define that now just for finite sets, and we'll deal with infinite sets later in the chapter. So this set, I guess I really don't need to tell you this, has size 4. The empty set has size 0. The size of a set is also referred to as the cardinality of that set. And we're going to use that word quite a lot when we talk about infinite sets. The Boolean operations on sets include union, intersection, set difference. I have a feeling you've seen these before, so I won't dwell on them. The union of two sets is the set of all elements that are contained in either set. But there is an important issue here. X is in A or X is in B includes the possibility that X is in both. It's the inclusive OR that we use in mathematics, not the exclusive OR. That's a little bit different than perhaps common English. If I said to you, today I'm going to the bank or the grocery store, you might infer that that means I'm going to one of the two, but not both. And that's not really correct. It would be, if that's the intent I wanted to convey, I would have said, today I'm either going to the bank or the grocery store. I might even add, but not both, one or the other. In mathematics, the or is always inclusive. So the statement, I'm going to the bank or I'm going to the grocery store, is true if I go to both. We'll talk about this again when we talk about logic, but it's important to make this distinction. The intersection of two sets is the set of all elements that are in both. The set difference, A minus B, some authors will use an ordinary minus sign here, but I prefer this symbol, which is commonly used for the set difference, because it reminds me I'm not dealing with numbers, I'm dealing with sets. It's defined to be the set of all elements in A that are not in B. And it is also called the relative complement of B in A. So be careful here, there's kind of a swap of the two letters A and B. So here's a simple example. If you use the definition, it's the set of all elements 1, 2, 3, 4 that are not in this set. So it's just 1, 2, and 3. The fact that 5 and 6 are here is pretty much irrelevant. But the point is that B does not have to be a subset of A for this definition. The union of all the sigmas from sigma naught to sigma n is gamma n. And gamma n minus sigma n is gamma n minus 1. Let's talk now about disjointness. Two sets A and B that have no elements in common are said to be disjoint. So in symbols, the intersection is the empty set. So for example, when n and m are different, sigma n and sigma m are disjoint. No words can have length n and length m at the same time. But the sets gamma n and gamma m are not disjoint. In fact, one is properly contained in the other. So their intersection would be the smaller one. Disjointness can easily be extended to more than two sets. But it turns out there are two different generalizations, both of which are important. In fact, one generalization is sort of a direct generalization. That's the lesser important one. So here's the definition. We have a family of sets. This family is disjoint. We'd also say that the sets are disjoint if their intersection is empty. So that is the most direct generalization. But a family is pairwise disjoint or mutually disjoint if no two sets in the family have any elements in common. Every pair of sets is disjoint. So that would look like this, where I is different from J, and they range from 1 to n. Now, it's critically important to understand the difference between these two. Disjointness is much weaker than pairwise disjointness. It's much harder for a family of sets to qualify as being pairwise disjoint. And here is a simple example. Let's take these three sets. They are disjoint because their intersection is empty. They satisfy the weaker condition, but they are not pairwise disjoint. For example, the first two sets have the element 1 in common. So they don't qualify for the stronger condition of being pairwise disjoint. You could argue that pairwise disjointness is a more important concept. That's debatable, of course. If sigma is an alphabet, then sigma naught, sigma 1, sigma 2, these sets are pairwise disjoint. This is an infinite family, so the concept of pairwise disjointness works just fine for infinite families. Okay. Related to disjointness is a concept that I like very much, but you don't see as often as I think you might. It's not really a new concept. It's just a definition. Disjoint union. When two sets, A and B, are disjoint, I will refer to their union as a disjoint union. This is just terminology. It's not new mathematics. And I'm going to use this symbol, which is somewhat common. Others use different symbols to denote a disjoint union. And let me put the union symbol in here so you can see the difference. The union symbol has a round bottom. The disjoint union symbol has a square bottom. So you'll have to be very careful when you're handwriting these to make it crystal clear which union you're designating. Whenever you see this expression, whenever you see this symbol in this book, it is with an understanding that A and B are disjoint. If A and B are not disjoint, I will never use that symbol. Okay. And of course, the cardinality of the disjoint union of two sets is the sum of their cardinalities. Given a set A, we'd like to be able to talk about the set of all elements that are not in A. But there's a little catch here. Before we can do that, we have to specify the set of candidates for not being in A. I call that set U because it's generally referred to as a universe or the universal set for this particular operation of taking the elements that are not in A. So the set U minus A, the relative complement of A in the universe, is just called the complement of A. It's a little bit of a dangerous term. It's denoted by A super C. It's dangerous because if you just say, here's a set, tell me what the complement is, the response should be, well, I can't tell you that until you tell me what the universe is. Okay. So for example, if this is the set, and if the universe is the set of all positive natural numbers, then the complement of A starts at 4, 4, 5, 6, and so on. It's everything in U that's not in A. But if the universe is a set of integers, the complement is considerably larger. Okay. So the complement depends on the universal set. The relative complement, A minus B, can be written in terms of intersection and complement, but again, this only works if A and B are subsets of the same universal set. The concepts of union, intersection, and so on, relative complement, can be described using pictures. They're called Venn diagrams, named after a British mathematician named John Venn. This is the Venn diagram for two sets. You always need to mention and include the universe. Okay. So A and B are subsets of the same universe. This shaded part, the blue portion here is the union, here the intersection, here the relative complement of B and A, and this is the complement of A. The Venn diagram for three sets would look like this. We're not going to have a lot of use for Venn diagrams, but at least I felt I should mention it. Once you get past three sets, Venn diagrams become fairly useless unless you can figure out a way to draw four sets and all their possible relationships in the plane. It's not so easy to do, maybe impossible. Certainly not as circles, would have to be more complicated shapes. Here are the properties of the Boolean operations. I'm not going to go through all these. You can read them yourself. Many of them are analogs of properties of arithmetic, commutative property, associative property, distributive property. Some are not, like the idempotent property. But you should pay particular attention to De Morgan's laws because they're extremely important and are sometimes a source of confusion for students. If you want to take the complement of a union B, it is the intersection of their complements, not the union of their complements. Union becomes intersection when you distribute the complement operation. And similarly, intersection becomes union. I would strongly urge you to think about this until it makes sense to you. Draw some Venn diagrams if that helps, because you do not want to make the mistake of preserving the union or the intersection on both sides. You have to swap the two operations. Here are a couple of examples of the use of De Morgan's laws along with the other properties of Boolean operations. And I'm going to let you sort through this. What I would do is write this down on a piece of paper and try to finish this one, and especially do this one without looking at my solution here. Because it's important to practice this. It's not that difficult. Once you get some practice in, you shouldn't have much trouble. Here is a proof that the left distributive law holds. Generally speaking, the way you show that two sets are equal is to show that each one is a subset of the other. So it would be to show both of these inclusions hold. And it's not a very long proof, so this too I will leave for you to construct. Let's talk now about the Cartesian product. Also, I have a feeling you've seen this before. Given two sets A and B, we can form the set containing all the ordered pairs, denoted this way, where little a, the first component, belongs to the set capital A, little b belongs to capital B. This is called the Cartesian product of A and B, denoted by A cross B, and here it is in symbols. Little a is in A, little b is in B. The Cartesian product of a set with itself, A cross A, is sometimes denoted by A squared, so it would look like this. And we can extend the Cartesian product to more than two sets. It's what you would expect. A cross B cross C is a set of ordered triples, where little a comes from capital A and so on. And here it is in more generality for the Cartesian product of any number n, finite number of sets. There is a definition of Cartesian product for infinitely many sets, but since we don't need it in this course, I haven't included it. Here are some examples which I'll let you look at. Something you may not have seen before is the following. I've made a point of saying that mathematics requires great precision, and that includes, of course, in the forming of definitions. So what exactly is an ordered pair? How do you define ordered pairs using the ZF axioms of set theory? Well, the first thing to realize is that order is not the real issue in an ordered pair, despite the name. It's the distinguishability of the two components, the two parts of an ordered pair. It doesn't matter that one comes first, reading left to right. That's not the issue. The issue is that you can distinguish between the two components. The most common language is to say little a is the first component, little b is the second component. That's because you generally read from left to right. But it's not to imply that somehow A comes before B in some sort of intrinsic order of the elements. It's just the left to right reading order. So in fact, you could write ordered pairs in a lot of different ways. This is the most common way, of course. This is fairly common too, as a vector of size 2. You could conceivably write an ordered pair in this form as a diagonal matrix. A bar B would work just as well. So would these. I don't recommend any of these notations, but the point is, look at this one for instance, you can distinguish between the base and the exponent, and that is the key property. So the key property of ordered pairs is really that two ordered pairs are equal when corresponding components are equal, when the components match between the two ordered pairs. And this is the definition of equality for ordered pairs. So it looks like this formally. Ordered pair AB equals ordered pair CD if and only if A equals C. In this case, the first components are equal and the second components are equal. In this notation, it would be the top components are equal and the bottom components are equal. Or in this notation, the upper left components are equal and the lower right components are equal, and so on. Now comes what I think is the interesting part. There have been several proposed definitions for the notion of an ordered pair. And some of the most renowned mathematicians of all time, the most famous mathematicians, the sharpest guys, have proposed definitions. And as you would expect, each of these proposed definitions satisfies this key property. Also, in all the cases that I'm going to show you, one direction of the if and only if is pretty obvious. If the components are equal, the ordered pairs are equal. So I'm not going to speak further about that. It's this direction that is the most interesting. If two ordered pairs are equal, then the components have to be equal. So the first proposed definition we'll look at is from a mathematician and philosopher named Norbert Wiener. In 1914, he suggested the following definition for ordered pair. So I put a W subscript here to denote the fact this is Norbert's suggestion. It's rather a complicated looking suggestion. A lot of brackets. Let's check the key property. If two ordered pairs are equal, we need to verify that A is equal to C and B is equal to D. Well, the first thing to notice is that these sets have a doubleton subset. One of its elements is a doubleton subset. The other element is a singleton subset. And not to be confused here, this is a singleton subset. How do you tell? Well, you look inside the outer brackets and you look for commas. One comma would mean two elements. No commas means one element. The only element of this set is itself a set. It's a singleton set. This is a doubleton set. It has two elements, this one and the empty set. These can never be the same because regardless of what A is, that is not the empty set. So the first thing to notice in matching these two, remember what it means for two sets to be equal. It means they have the same elements. It's not possible for one of the doubleton elements to be on one side to be equal to the singleton element on the other side. Because if this was the case, then since they have to match element-wise, this would have to be a singleton. This would have to be a singleton set. In other words, these two elements would have to be the same. But I just got through saying they're not. They're obviously not, because this is not the empty set. So this equality implies that the doubleton sets must be equal and the singleton sets must be equal. Well, this implies immediately that B equals D, because the elements have to be the same. And similarly, the elements have to be the same over here, but one of the elements is the empty set. Those match, so we have to have set containing A equals set containing C, which means A equals C. So the key property of ordered pairs is indeed satisfied by Norbert Wiener's definition of ordered pair. Norbert Wiener is considered the originator of cybernetics and was instrumental in the development of modern artificial intelligence, of which we are all plagued these days. That's a little unfair. I like artificial intelligence. I find it very useful, but only in a very limited way. and only with great circumspection. The first time I asked ChatGPT about me, it said I was a math professor. I wrote a number of books, but unfortunately I died in 2019. So that was a little startling. I taken aback a bit by that. I think that's been changed now. So I'm glad to hear I'm not dead. One more little anecdote about Norbert. He told a friend of mine, who was also a friend of his, one day they were driving in a car from Los Alamos Labs to Santa Fe, or perhaps the other way around. I don't remember. He turned to my friend and said, you're not a first-rate mathematician. I thought that was kind of brutal. My friend was a first-rate mathematician. In any case, let's move on. The next candidate for ordered pair was proposed by Felix Hausdorff. And he suggested this definition, specifying that 1 and 2 are distinct sets different from A and B. So that's a little awkward, because what if A is 1? Then you'd have to change this symbol. And what would you change it to? I don't know. So there's something a little sort of concerning about this definition, but I'm not suggesting I would ever contradict Felix. He was a much better mathematician than I am. I'd love to be able to ask him about that, but it's too late. This definition does make it rather easy to show that the key property of ordered pairs holds. If these two sets are equal, these two ordered pairs are equal, then the elements have to match up. Well, this element is the only element of the set on the left that has a 1 in it, so it's got to be equal to this one. So A1 has to equal C1. The 1's match, therefore A has to equal C. And a similar argument for the sets that contain 2 shows that B equals D. So that was fairly easy, and that's a virtue of this definition. Hausdorff was a German mathematician who's considered to be one of the founders of a modern field of mathematics called topology. It's a terrific, really interesting branch of mathematics, one I particularly like. I haven't taught a course in it since the 1980s, when I taught a graduate class in topology, but it's a really fun field. He also contributed significantly to the fields of set theory, measure theory, and functional analysis. Unfortunately, this is a very sad story, he was forced to give up his academic position during World War II by the Nazis. And he was told that he and his wife would be moved to a camp. So he, his wife, and his sister-in-law committed suicide on Sunday, January 25th, 1942. Our next candidate comes from Kazimierz Kuratowski in 1921. And his proposal looks like this. It's nice and clean. I might almost say elegant. Certainly a lot simpler than the previous proposals, especially Norbert Wiener's proposal. And it's also fairly straightforward to show that the key property of ordered pairs holds. And I'm going to leave that for you to think about. I'm not going to go over this. You have it here if you need to look at it, but give it a try yourself. Kuratowski was a Polish mathematician and logician who contributed significantly to topology, publishing over 170 works. During the war, he taught at the underground university in Warsaw because higher education for Polish citizens was forbidden under the German occupation. There is a slight variation on Kuratowski's definition. Instead of a singleton set A here, just the set A. And this too makes it simple, even simpler, to verify the key property of the ordered pairs. So the winner. One of these suggestions has won out and is now the common definition of ordered pair. I resisted saying, and now the Wiener, and now the winner. It's Kuratowski's definition, which looks to me, based on what we've just discussed, to be the simplest and easiest to remember. It's the singleton set containing the first component together with the doubleton set containing both components. So it should be pretty clear that you can distinguish the first and second components. The singleton set tells you the first component, and then the doubleton set, by elimination of the first component, gives you the second component. So that's a nice, neat definition. And it can be used to extend the definition to ordered n-tuples in general. An ordered triple is an ordered pair where the first component is also an ordered pair. And you can do the same thing more generally. The final topic in this chapter is that of partitions of a set. Loosely speaking, as you can see in this figure, a partition of a set S is a dividing up of S into non-empty, non-overlapping subsets, which are called blocks of the partition. And the union of the blocks has to be all of S. And here's a somewhat more formal definition. Let S be a non-empty set. A partition of S is a collection of subsets of S with the following properties. The subsets are non-empty. They are pairwise disjoint, in other words, non-overlapping, and their union is all of S. In this case, the sets B sub I are called blocks of the partition. And I'm going to denote the set of all partitions of S by part of S. And all the partitions of S that have exactly K blocks with a similar notation with the subscript K. Here are some examples. This is the set of numbers from 1 to 8. These three subsets form a partition. They're not empty, pairwise disjoint. Their union is all of A. This is also a partition of A into 4 blocks. This is the same partition. The blocks are identical except in the order in which they're written and also their designation. I use capital C's here and capital D's there. And I did this for a reason. These two partitions are the same because the order in which the blocks are written is irrelevant. There's no sense of order among the blocks. For an alphabet sigma, the set of or family of subsets sigma naught through sigma n forms a partition of gamma sub n. But the subsets gamma naught through gamma n do not form a partition. Now I need to make something as clear as I possibly can. The blocks of a partition are considered to be indistinguishable. Now that seems a bit strange perhaps, because in the previous examples I've identified the blocks using distinguishable labels. D1, D2, D3, and D4. But that wasn't necessary. So for example, if you look at this, the set A, which is the set from 1 to 8, this is a partition. It's a family of subsets that fit the definition of partition. And I haven't assigned letters or symbols to the individual blocks. And as you know, the elements of a set, their order doesn't matter within the brackets. As long as they're separated by commas, it doesn't matter what order you put them in. So it's probably better to think of a partition in this way rather than in this way. Nonetheless, this is common notation because when we're speaking, it's easier for me to say, for example, look at block D3 than it is here to say, well, look at the block containing 6, 7, and 8. So it's a notational convenience, but it's not a mathematical issue. I'll say again, the blocks of a partition are considered to be indistinguishable, even though we may artificially distinguish them by assigning symbols to them so we can talk about them more easily. It may also seem a bit strange because two blocks of a partition would be distinguishable if they have different sizes. But what's really permitted to say is only something like a partition P has a block of size n and a block of size m. Otherwise, there's no way to tell which block has size n and which has size m. So this is a little bit subtle and confusing because the very nature of writing down something on paper makes the elements of that something distinguishable by their position on the paper, for example. And that's not inherent to indistinguishability. It's artificial distinguishability, if that makes sense to you. It's worth thinking about this because it's going to come up later. We will be talking about divisions of a set into subsets where the subsets are distinguishable. So I can't call those partitions. Finally, for various purposes, such as counting the number of partitions of a set, which is something we're going to be interested in doing, the nature of the set S really is irrelevant. Whether the set contains letters, numbers, symbols, it doesn't really matter. If a set has size n, it will have a certain number of partitions regardless of the identities of the elements, numbers, letters, and so on. So oftentimes I'm going to use this set when I'm talking about things like how many partitions does a set of size n have into k blocks. It may as well be this set. It's an easy set to use. Okay? But whatever I say would apply to any set of size n. Okay, that's the end of chapter 1, and that should be the end of this video. Thank you for watching, and I hope you found it interesting, and I hope to see you in the next video.